Thanks, Jim. I'll try to do this without messing up the computer. They tell me it's working now, so.
I can come up and switch.
No, it's okay. I think I can handle it. So it's always fun to be the first speaker after lunch, right? So I have to try to dance or something so people don't do headers into the desk. So no, don't dance. All right. Okay. So as Jim said, we actually got both. I think Ian's talk and also Jason's talk were a nice setup for this session on ecohydrology, which is really just talking about the relationship between flow and changes in flow and how it affects the in-stream biology. And so what I'm going to do is start by just giving you a little bit of a broad overview on the topic and sort of queuing up the speakers that come after me. And then the speakers that come after me actually have the hard work because they actually have to tell you the technical details. I just have to sort of set up the question, so I have the easy job. And then we'll finish up with Jeanette Howard at the end, who's going to bring it all together for us and tie it in a nice bow and answer all the questions. So that's that. No pressure, Jeanette. Okay. So I want to start by saying that, like you've heard during the USGS session, all of this work is, by nature highly collaborative. It's very interdisciplinary, and so we have a team. There's some logos up there of some of the folks that we've sort of formed a ad hoc work group through the state to try to sort of get our heads around these issues of how to understand relationships between flow and in-stream biology and how to develop predictive tools and management tools to help us hopefully do a good job of managing flow in a way that ensures biological integrity of the streams. And so that's what this session is going to be focusing on. All right, so I don't, hopefully this is sort of, like a colleague of mine says, sort of stating that the rear end of a pig is made of pork, right? So hydrology is important for streams, right? That's pretty much obvious, right? And it's a key driver because, as you heard, and I think actually Ian's talk showed some of this, that the physical habitat and a lot of the physical parameters that the in-stream biology, particularly the benthic invertebrates and fish are responding to, are driven by hydrology, right? So changes in flow patterns are going to drive the hydraulics and the physical substrate characteristics of the stream, which in turn is going to affect the biology. So if you sort of work that in reverse, what that means is if you can manage the hydrology in an effective way, then you're taking a big step forward to trying to manage the stream to ensure biological integrity. And that's what this whole thematic area is about understanding those relationships and trying to sort of accomplish what we're showing in this flow chart. So we also know that we do a lot of things on the landscape to mess up the hydrology, right? We're actually really good at that. So everything from agriculture to timber to, one of the new players on the horizon, cannabis production, which, has a lot of hydrologic impacts on the system. We have stormwater management, and then we have all the things that we do in terms of floodplain encroachment and urban effects and things like that. So there's lots of impacts and lots of ways that we impact the hydrology. And each of these different sort of mechanisms of stress has a different way it affects the hydrology, right? It affects different aspects of the hydrology. It might affect base flows or peak flows or recharge. And so understanding how the different stressor affects the different mechanistic parts of the hydrograph and then how that translates to biological response is pretty complicated. And so that's what we're trying to tease out. And so working with our collective team, a lot of the people who you'll hear from today, we've started to develop this framework for understanding how do we start to put the pieces together. And really, if you think about each of these boxes, there's a set of tools in each of these boxes that we have to develop to help us be able to understand and model and predict hydrologic change, how that translates to ecological change, how we can use those two things together, the combination of the relationship between hydrology and ecology to set some sort of targets or management targets that we might want to do in terms of how we manage flow. Obviously, we have to balance that with all the other things that affect flow, like consumptive uses and other types of stormwater management, other types of beneficial use needs, flood control. And then obviously we have to try to implement that through some sort of policy that's implementable and interpretable and hopefully doesn't wind up in court, which that never happens. But And yeah, I put this slide together because I think it's important, in this workshop in particular, and I think this is true of pretty much all the things we do from bioassessment to ecohydrology, that it touches lots and lots of programs. And I put a few of them up there. This is not an exhaustive list, but I think it's important to keep in mind that there are many water, and these are really water board programs, so I haven't sort of broadened the horizon to talk about the variety of federal programs like FERC relicensing and some of the 404 wetland programs, et cetera, but there's a whole bunch of programs that are touched by these relationships. And so it's really important when we develop these tools to be thinking about what is the interface between these tools and all the various programs that hopefully should be using the data and the tools, or to borrow a phrase from Pete again, is the data we're producing is the engine, right? It's driving all of these programs, and so we have to think about what those interactions are and how to translate that. So what is this all about? So what are you going to hear in the next 3 or 4 talks is really fundamentally we're just trying to do this very simple type of, establish this very simple type of relationship. We're trying to understand some change in flow and how that change in flow translates to some likely biological response in a community of interest, which again could be bugs, could be fish, could be algae, depends on the stream type and what our management needs are. But generating some sort of curve like this and then deciding where at the inflection point of that curve is an appropriate place to set a management target, that's really what we're trying to generate. So the trick is, like, how do you do that, right? So there's lots of ways people have tried to do it. You'll hear about some of those today. There's some methods that have looked at simulating the physical habitat responses and translating that to life history requirements of certain target organisms. There's a presumptive standard, which basically looks at some distributional measures of the hydrograph and says if you're sort of within 15 or 20% of the shape of the hydrograph, that's probably within the tolerance of the system. Sarah Yarnell is going to talk about functional flow, so I won't say much more about that except, looking at pieces of the hydrograph and how they relate to different life history requirements of certain organisms. And then Rafael Mazor is going to talk a little bit about the ecological limits of hydrologic alteration, which is another approach I'm going to talk a little bit about, introduce that, but looks at relationships between changes in flow and changes in biology at sort of larger spatial scales. So there's lots of different ways you can do this. And so what you're going to get in the session, the talks that come after me, is a little more detail on some of these methods, and then at the end we'll talk about how do you sort of put this together and decide what's the right tool to use based on the situation you're dealing with, the type of stream you're in, or the type of biological community you're interested in, or the management target. And so these are some of the considerations when you think about what tool should I use. Should I be using a hammer or a screwdriver or a wrench or whatever? Or my kids probably use the hammer for everything. It has to be scientifically defensible. We have to think about what type of stream, what's the endpoint, what's our management need. So all of these filters we have to run through and use these decision points to decide what's the right method. And so what you'll get today is a little sampling of methodologies and some thoughts about how to make the right decisions about which tool to use. Because it's, like you always hear, it's the not one size fits all, right? It's really kind of an ensemble of tools that have to be used together to solve these problems. And so when we think about how to apply this at the scale of a region or the statewide scale in a place as complicated as California, we have many sort of challenges such as, and you've heard some of these already, like how to deal with the immense heterogeneity we have in the landscape, how to deal with all of the ungauged streams, which are most of them, and how to assign flow targets when you don't have gauges there or gauging data. How do you know what endpoints from both the flow and biology, and how do you use all that and translate it to informing management decisions? And you'll hear a little bit about all of these things in the talks that come after me. So I'm just going to introduce the issue of classification because I don't think the other speakers are going to touch much on this, except to say that one of the tools that we do use to deal with some of the heterogeneity in the landscape is classification. And again, Ian touched a little bit on this in his talk as well, that one of the ways we can deal with this is by putting streams into categories based on hydrologic similarity and basically looking at flow ecology relationships within more homogeneous stream classes. And that's so that's one of the things that's a good starting point for a lot of this. And this map is the result of a collaboration that we've worked on with the folks in Southern California and the folks at UC Davis to try to develop sort of an integrated framework or an integrated classification system for streams in the state of California. And so we've used these different properties and we've come up with these different stream classes. And so this this has all kind of been put together and will hopefully be made available pretty shortly through a GIS layer that people can download and start to look at relationships within these individual stream types. So just to kind of finish up my introduction, I'm just going to give you a little bit of a preview of some of the methods you'll hear about today. Again, Sarah's going to talk about functional flows. Rafi's going to talk about the flow ecology approach using the Aloha. We actually don't have anybody today talking about the modified percent of flow approach, so I'll give you a couple of slides just to introduce that, and then I'll turn it over. So my 1 or 2 slides on functional flows, again, this idea of looking at different components of the hydrograph and setting targets or metrics based on life history traits of certain characteristic taxa, such as fish. These might vary by the geomorphic setting that you're in, so depending, you have to sort of take geomorphic setting as an important component of that, and so that plays into how you think about functional flows. Rafi's going to talk about the Aloha framework, this is sort of the characteristic Poff et al. Diagram that's been developed, and some of the key things about the Aloha process is it builds off the classification, which I talked about, and it's a little bit different than the functional flows in the sense that it looks more a community response versus sort of individual target organisms. It looks at responses of an entire biological community, and Rafi will talk more about that. These are some of the features, as I talked about, and it's a framework that you can use to sort of balance, in many ways, flow needs or ecological flow needs with other management needs. And this is kind of the type of response that you get where you can look at change in some sort of hydrologic method, metric, as a function of change in some sort of biologic metric, in this case our California Stream Condition Index, and you can look for, where does this relationship drop below a certain threshold value, like a CSCI of 0.79, and then use that to establish some flow targets. So that's kind of the idea behind how you use these biological community measures that are driven by this large bioassessment data set that we have in California to understand these relationships between changes in flow and changes in biology. And then finally, the modified percent of flow approach. Again, we don't have a talk on this today, but a lot of this work has been going more up in the northern part of the state, and Cal Trout has been involved with this. And this is an interesting approach which looks at the cumulative daily diversion volume. So the idea here is you're trying to not focus so much on the rate, because the rate can be variable, but how much volume can you remove from the stream at any given time during the annual hydrograph in order to maintain the integrity of the stream. And so it operates on this concept of about a 5% decrease in stage, which empirically the authors have shown translates to about a 10% reduction in stream flow. So they look at volumetric allowable volume removal that doesn't decrease the stage by more than 5%, and they sort of set that as kind of a target for how much water you can pull out of the stream. And so some of that is based, this is one of the graphics out of their report that relates stream flow in cubic feet per second. This is riffle crest thaw wag, which is sort of a surrogate for stage or depth. And they're just relating this to different fish passage and the probability of allowing fish passage to occur during a certain change in the depth of the stream relative to stream flow. And that's, you sort of translate that onto the hydrograph. I'll just click through this quickly. And what's shown in shading here, this is the amount of essentially volume of water that you could take out of the stream at any point of the year in order to ensure that your stage is not decreasing below a level that is going to cause an adverse effect to, in this case, fish. So again, that's just another way. And so what I've tried to show is just these are 3 different ways that you can approach how to deal with setting flow targets, and you'll hear a lot more about each of them in the subsequent talks. And so the roadmap for the session, I did include you, Ted. Oh, God. I was telling Ted right before this, I couldn't remember whether I included him or not because the problem is I put this talk together last week, and if I had put it together last night, which is what I normally do, then I would have remembered, but I didn't, so. All right, so you're going to hear about Rafi next, and then Sariana, who I've mentioned. Then Ted's going to talk about assessing hydrologic change at sort of a larger scale and different metrics and which ones we can predict well and which ones maybe we don't predict so well, and he'll talk about the predictive ability of some of those flow metrics. And then finally, Jeanette. I know it says Julie Zimmerman in your program, but she wasn't able to make it today, so Jeanette Howard from the Nature Conservancy, and you've heard Jeanette's name a couple of times today already, is going to wrap up by sort of bringing it all together. And then we have time at the end for some discussion with all the speakers, so hopefully we'll try to stimulate some ideas and questions and maybe a little bit of controversy, and then you can ask questions of the speakers after we're all done. So with that, I'm going to, unless there's any burning questions, you're going to hear a lot more about this by the other speakers, so don't ask me any questions because I don't have any answers for you yet. Okay. All right. All right, so our next speaker is Rafael Mazur, who works with me at SWRCB, and he's going to talk about the flow ecology using the Aloha approach.
I would say based on the Aloha approach,
Based on the Aloha
but not as